Hello, everyone. Welcome to our last class in the ray tracing course. Before we begin, let me read you this ACM policy against harassment. This live stream is moderated by ACM SIGGRAPH. We ask that all comments stay respectful of others and respect ACM's policy against harassment. This means to exercise consideration and respect in your speech and actions. Refrain from demeaning, discriminatory, or harassing behavior in speech, and please be mindful of your fellow participants. All right, so we are into the home stretch. This is our last class. And if you have been following along for the last 6 classes, today we will wrap up. We'll cover some soft shadows, and I'll give you some pointers to where to go to learn more and keep learning, because so much information out there. I was just talking to Eric, who's backstage, just like how much information is available to keep learning and experimenting. So let's bring in our guest, Eric Haines. He is an expert in computer graphics. He has been in this field for a long time, and he currently works at NVidia and has written several books. And let me just bring him in. Hi, Eric. Welcome to the class.
There. Hi, Rajesh, and hi, everyone.
So thank you for being here and spending some time with us. I'll ask you the same question I asked every guest so far, just about your background, how you came to be in computer graphics, and what all you have done and what you're doing currently.
Yeah, for me, it was definitely accidental. I mean, so I graduated from Rensselaer Polytechnic Institute in 1980, and computer science, okay, but I really had, and the job that I sort of got right after that was to work for RCA Astroelectronics, which was all about satellite launches and all that kind of stuff. I had a really strong interest, or still have a strong interest, in astronomy and just space and so on. But while I was at RPI, about the last year or so, I sort of latched onto a bunch of people who were in the computer graphics lab that had just started up there, and someone had, and I wasn't particularly interested in computer graphics, but someone had written this cool multiplayer, tank war kind of game, and just on vector graphics displays, but it was real time. It was like, oh, this is cool. And so through that, I got to know a guy named Al Barr, who is at Caltech and has done a ton of work. And but at the time, he was just a grad student who was working in biology. And he was saying, well, he was trying to make movies of, believe it or not, of a spermatozoa and how their tails move and how they wiggle around and so on. And so he was making these cool 3D forms, and he was finding, oh, well, if I use this ray casting technique, I get much cooler pictures than if I just try to turn it into some polygons and triangles and stuff. So he got totally sidetracked. It took him forever to finish his degree, but the rest is history. He became a professor at Caltech and did a lot of seminal work in ray tracing and in modeling and whatnot. But anyway, that sort of gave me the bug, or I sort of was like aware of it. So for a few years, I sort of did the satellite stuff. But I remember being in his apartment in Harvard Square, where he was a super minimal kind of guy. I think he had a desk and a table and a chair. So I was sitting on the floor, and I looked at the back of I forget if it was the SIGGRAPH Proceedings 1981 or 82, one of those, I think it was 82, where Rob Cook had these little sort of Hershey Kiss looking little objects, and they had all these amazing materials. And it was, for the time, it was like, he was using BRDS basically. He was using, how to properly reflect light and all that kind of stuff. And so he's getting all these different cool looking materials, and I was like, oh, I want to do that. So that was life-changing, basically. And and since then I've been in graphics ever since, one way or the other. I went to Cornell for 2 years and got a master's there, and then my advisor became my president. He had a little startup, Don Greenberg, and I worked for him for a while. And that company got acquired by Autodesk, and so I worked for Autodesk for a bunch of years. And to be honest, Autodesk laid me off at about 20 years. And I was in good company, frankly. I feel good about that because I'm like, well, me and 1,499 other engineers got laid off. A new CEO basically came in and decided to clear house. And so I felt good because I was in the company of one guy who won an Academy Award. Jos Stam won an Academy Award. So I'm like, well, all right, if he can get laid off and I can get laid off, great. That's a good deal. And so at that point, my co-author, I co-authored this book, Real-Time Rendering, now in its 4th edition, with this guy, Thomas Akinine Muller. And he's like, oh my gosh, you're laid off. You have to talk to NVIDIA right now, because this was before they had announced any of this RTX stuff. And so I did, and I'm like, okay, that's my dream job, and they'll let me not have to move to anywhere else. This is crazy ideal. So it was wonderful. It's just wonderful timing. And yeah, and so I've been with NVIDIA. I just came out. It's been 2 years now, actually, that I've been there. And yeah, that's been a blast. I got to work on Ray Tracing Gems, a free book. I will put a plug in for it, and rightfully so too. It looks like a good book. I only had a little consultation role in it, but Ray Tracing Gems 2 is coming out, and I just got the date today. It says August 4th. It'll be available for download for free, and they're much more focused on like sort of reference articles, like just not just like, oh, here, like the first book was sort of like, oh my gosh, there's ray tracing, let's get articles from anybody we can, and so it tended to be just kind of whoever wanted to write an article kind of thing. Everybody had the few groups and people who had played with RTX at that point, and so. This time around, they're much more focused on like, how do we teach people? And so looks to be a lot of good reference bits in there that I'm looking forward to actually taking some time and trying to just sit down with it all. It's a big book.
I'm looking forward to that too. Yeah, and I think we've been giving away some of the copies thanks to you. So it's pretty interesting actually, because I've followed like all the books. Like when the SIGGRAPH paper became like almost too difficult to read because of all the math and stuff,
right.
There were graphics gems at those times. I think those were wonderful books with small little techniques that you could readily apply. And then after that stopped after like 5 or 6 editions. I think you started the Journal of Graphics Tools, or
yeah, I was one of the
right.
founders, right.
So those were awesome, actually. So there's a little bit step up from graphics gems, but still pretty technical, things you could implement in a day or two. And now we have something similar again. What are you working with in terms of the graphics techniques?
What am I personally doing? Or
yeah.
I'm kind of all over the map. I mean, basically, like I say, I've been doing a little consulting for Ray Tracing Gems too.
Mm-hmm.
I'm doing again sort of little, like I got to play with a little bit. We're talking, I know people have talked about APIs, like Keith Morley was talking about APIs to make things easier and so on. Right. Ingo Wald, who's done a lot of ray tracing stuff, he's working on optics too, and he has this whole API that he's put together to right. make it a nicer wrapper, basically around the sort of more to the metal kind of. It's not really to the metal, but it's a little it's a little hard to get your mind wrapped around. Originally, the optics API, but he abstracts a lot of the little painful bits of that and has this nice wrapper around it called OWL. OWL. So anyway, if you play with optics, you might want to give that a look as a starting spot. So anyway, that's been going on. There's the stuff I can't talk about. The one thing that I have been doing a lot on actually is Omniverse, which is sort of it's kind of just a platform as a way to get simulation and all kinds of other things to tie into rendering, into a sort of rendering RTX-based kind of engine. What I like it for is the fact that it is really real time. I mean, I can just throw giant scenes in, and in either real time or near real time, I can move around and and get really pretty nice ray traces and find bugs. I think I found a lot of bugs. It's in beta, and yeah, no, it's I think Carl Lee talked about this a few sessions ago about use your own programs, and that's advice that I would give to anyone, is that if you're developing any kind of program, try to also be a user, or try to get other people to use it that you trust or whatever, that'll give you honest feedback and so on, because just that cycle of actually using the thing, you go, oh man, if there was just this one, one extra little feature, or if there's, and you have your own blind spots too, obviously, but I've certainly found that with my own, stuff that I've developed for hobbies or whatever, that, like I have this silly program that is now, I think it's gotten over 1 million downloads over the past decade, which was just a total hobby project. Called Mineways, which was just about Minecraft. It's just taking stuff from Minecraft and turning it into a mesh file. Very simple kind of idea, but people use it all the time for making animations and so on. And yeah, just you'll just find like, oh yeah, you just iterate and you sort of, one more little thing. This was so great, makes it so much easier, blah blah blah. So anyway, yeah, I highly recommend use your own program or get people to give you feedback on your own program, and branch out, try different things. Don't just get stuck in I'm a rendering guy, I only do rendering. I just knowing a little bit about the other fields is a huge help in sort of understanding what people need really.
And then also you taught rendering and ray tracing for many years to many people. Both in professional settings or to students. What kinds of things do you think people stumble on, or what advice would you have for kinds of things you think would be roadblocks to learning?
Yeah, it's tricky. I think part of it is, people have sort of mentioned this before, is you get hung up on the algebra or the equations or whatever. And trying to get an intuitive, some sense of that, before you actually sort of dig into the equations, is certainly a help. Trying to find programs that are interactive that let you play with those equations. I don't know, maybe 8 years ago, I helped produce a massive open online course, and for me, the most useful thing was just the fact that I could make JavaScript using 3JS, just making a simple 3JS thing. You could make little programs that would be like, okay, here's the matrix, and now look what happens when you rotate. This is the line in the matrix that's changing. Here's what happens when you zoom. These are the factors that are changing the matrix. And just trying to build up that kind of intuition is really, I find really helpful. And in fact, that's something I do a lot, actually, in my, well, not a lot, but a fair bit in my job is, we'll have some idea and we'll be like, oh, okay, well, we should try this or whatever. And it's like, okay, well, give me a day. I'll just make a little program in 3JS. There's no download, you just hit the browser button and there's the program running for you. And it lets you explore sort of geometric concepts just very naturally, lets you just start to play with things and go, okay, I think we could probably do something in this area, or, oh wait, this acts weirder than I thought. When I bend this spline, something really weird happens there. What's going on there? Or that kind of thing, that sort of trying to build up a geometric sense of things, or just a intuitive sense, has been a huge help for me.
Oh, that's awesome. And any other advice or anything else you want to talk about? I'll let you get on with your day, as it were. But let's see. The one thing that I was thinking about that I'll just my one bit of career advice. Because I've seen it happen a time and time again, where suddenly a web page goes away, and it's sad. Is right. That is for I highly recommend to everyone to get your own domain. Whatever you want to call it. Try to not make it too silly, but just something that you're willing to live with through your whole life. And you can always just once you get a domain, you can redirect that domain. If you have a professional page on your you're working at you're a professor at a university, or you're a researcher, or wherever you are, that you may already have, a web page somewhere through your company or your university or whatever. Well, you just redirect that domain to it. But, at some day, you're probably not going to be at that university or wherever. And at that point, then, hey, great, your page doesn't have to go away. Anyway, that's that's my one bit of advice, is because I've seen it happen too many times where some great resource just goes away because, well, I left the university, I never bothered to move my stuff over, and I never or even if I did move my stuff over, no one knows where it is because they don't know the URL. So anyway, I think it's like it's a resource that goes away that you want to use. I think it's a pain sometimes. So thanks for reminding me, because I was going to put all of my slides up in GitHub so that they stay there even after if they go away from the SIGGRAPH shared drive. So.
Right. Yeah. I think that'll be an interesting issue over time because, there's a lot of resources that are great. I mean, you mentioned like graphics gems. That's actually a repository that I actually maintain. And, the thing that I realize is like code, sometimes gets a little crusty around the edges and you have to do something to make it recompile. But, math, the underlying math, it doesn't rot, it doesn't go bad. And just having that available and having those little code snippets around so that you don't have to rederive how to, do a cubic spline or how to do whatever, is just, it's a huge plus for us all.
Also, like one thing I wanted to talk about or ask you is more about the hardware side of things. So I know you work with optics and RTX or CUDA directly. What are the main challenges there? I think that sometimes the learning curve is super steep. So people who want to get into that, what should they look at?
Yeah, it can be tricky, and like I say, people are trying to come up with tools like the OWL API that I mentioned to try to make it, a little less crazy. So yeah, if you're trying to get directly into it, it's yeah, I don't know. I haven't seen. I've been waiting for the good resource on that in a way. Like there are code repositories, and Microsoft has some good samples with DirectX and so on, and those are a good starting spot. Is you just sort of take one of those and try to modify it and so on. But yeah, unfortunately, I haven't found the great resource. So maybe one of the people taking this very course, will be the one who finds some time to actually go make that good resource. Because honestly, I think that would be really valuable. But for me, actually, the exciting part is just the fact that with hardware, I mean, that's what's great about this field is, just when you think it's all like, oh, it's kind of settled down, and we know a lot of theory that's not going to change and so on, but something new happens, like, oh, well, there's VR hardware a few years ago. Okay, that sort of changes the playing field, or RTX comes up. Oh my gosh, that changes the equations of what's doable and what's not. People mention time and time again machine learning. How does that influence things? We talk about ray tracing as like, well, we can sample, off of a surface in any, a zillion directions to try to get the incoming radiance and try to, get a good BRDF kind of sample and so on, and that's very exciting to me as well. Can ML somehow work there, or, what are the limitations there and so on? And yeah, so there's just a lot of great stuff happening. I love the fact that the field really doesn't just, say, well, it's all just physics, we're done, it's that there's the efficiency is really what makes it, sort of drives a lot of things, really. We know the ultimate answer, you just trace, back in 1990, I used to joke with my coworkers, because we're working in ray tracing, we're like, someday we'll just shoot 10,000 rays per pixel and, it'll all be solved, and in 50 years we'll all be done. But, as we saw, like Brent Burley and other people talk about, well, every time you give someone, say, oh, we can shoot 10,000 rays, well, they'll put 10 trillion objects in the scene. So, suddenly you can't shoot those 10,000 rays anymore, and you have to denoise or come up with some other strategies or whatever. So, yeah, the race continues. It's exciting that way.
Well, all right. So thank you so much again for being with us, and then also for the books, actually. So I think that's given a little bit of a motivation for people to do the homeworks and create some interesting scenes. So thank you again.
Yeah, well, thank you for this course. This is wonderful that you're doing this.
All right.
Bye now.
Bye-bye. All right, that was Eric. So he had a lot of good advice. Again, if you look back at all the people I've talked to as guests on this class, I think you'll see a similar thread of advice where you focus on just getting a good understanding, good basics, and then start coding a little bit and go back to the math, understand that. So you go back and forth. You don't want to sit there and read a big tome about the math and then try to implement it. Just go back and forth, try to build up theory and then also observe, because ray tracing is an observable thing. You can look around and see how light reacts. You can create situations that are difficult or interesting and see what is causing that. So it's a physical phenomena that we are trying to simulate. So you can always replicate that physical phenomena somehow, caustics in the pool or strange lights or colored lights. So there are lots of possibilities where you can try things out and see why things work or why things don't work. So what we'll do today, we'll do a little bit of recap. We'll talk about a little bit of soft shadows and BRDF sampling, and I'll wrap up and we'll give you some pointers to learn further. So just some housekeeping. You know now where the slides are, where the shader toy profile is for me, and just go there. There is a new shader today called Soft Shadows, and you can take a look at that. So before we dive into the material for today, I want to thank all the guests. It has been a great pleasure for me personally to come talk to them. Most of them are my heroes growing up, learning graphics from these people, their articles, their papers, their books, their classes, and having the pleasure to work personally with Brent and Carl and Keith over the years. So it's been an absolute pleasure for me. It's like talking to friends, and hopefully you gain some insights from them directly. This is a wealth of experience they have, and I'm so thankful that they were able to take time to share that with us. Also want to thank ACM SIGGRAPH for making this course possible. So when we started out, so I think we had this goal of making this course free to everyone, and have the course be a little bit longer course so that we can dive into things and actually do programming and learn a little bit incrementally, rather than give you this dump of here's computer graphics, here's ray tracing, this is how to do it in a 2-hour course. So we were able to do this day after day. So there's a army of volunteers who are behind the scenes making this possible. They are with me every time I present here. So it's a lot of effort. So 7 classes, that takes me about 4 hours per class to prep and present. And along with me, all these volunteers are there behind the scenes during for the same time. So all for the love of teaching, because I like teaching, and I hope you got a lot out of it. And having said that, let's get back to the course part. So we did shadows last time, and I'm trying to see if I can describe to you like how shadows are formed. And most of us know how shadows are formed. You have some object that is in between the light and ground, or whatever object shadow is falling on. And when you have something like that, you can see that from the point of view of light, if you trace these rays at the edges of the object, you get this area that is in shadow. So that's normal. That happens every day. Objects, you look at the light, you can just look at it right now. If any light source, place a hand on it and you'll see the shadow form. So we did that last time. We said from the ground, which is where the object was hit with a ray, we look back at the light. And if we can see the light, which means it's not in shadow, which is all this area. And if we cannot see the light, it is in shadow, which is all this turquoise colored area. So then on the right side also, because you can see the light from this point, you have everything else here is not in shadow. So all this turquoise area is in shadow. But if you look at it now, like it's a binary situation, right? It's either in shadow or not in shadow. And that is well and good for point lights like this, where it is one point source and it is where all the rays are coming from. So in practical situations or in everyday situations, most lights are not sharp point lights, right? So the lights have area. And what you have is something more like this. So in a light that has a bigger area, you'll see that the rays that come from the light, they fall into 2 categories, this reddish one and the dark colored one. So in the reddish region, you can partially see the light. In the dark region, you cannot see the light at all. And outside of those, you can see the light fully. So this kind of situation is what causes soft shadows, actually. So because you're only partially seeing the light, this area is partially in shadow, and we have names for this, penumbra and umbra. So umbra is shadow and penumbra is almost shadow. So this is, in a real life situation, you'll see that it's very common. And also you can see that if you move the object towards the ground, the penumbra starts narrowing, right? So as you move this object down towards the ground, you'll see that the angle that the penumbra is making, it becomes narrower and narrower, so which means the shadows get sharper and sharper and darker until it's all covered by this object and you cannot see the light at all. So that's also a natural phenomenon that's covered exactly by this reasoning, is that because normal lights have areas, and then when you're partially seeing the light, you're able to get those. So that's how you get soft shadows. So for us, then the question arises: we cannot do just a binary comparison, whether you see the light or not. You have to kind of understand like how much of the light you see, not just whether you see the light or not. You want to be able to figure out how much of the light you're seeing. And specifically, you want to figure out the area that is subtended by the cone that is causing this penumbra. So at each point of the intersection, you would then basically form a cone that encompasses the light, and then you try to find that projected area. So the amount of shadowness, if you will, depends on how much of the light you can see. So that's how we get soft shadows. And speaking more mathematically, what we want to do is figure out this cone and sample that cone, essentially. So you want to be able to take the ray that goes through the center of the light and perturb it a little bit just within the cone, and find that new direction. So this is very similar to BRDF sampling. It is essentially exactly the same thing, except you're now sampling the light. And lights can have different shapes. We are mostly going to be using spherical light. So this formulation for sampling a spherical light essentially forms a cone and then takes that ray towards the light and then perturbs it slightly. That gives you the new direction. So if you remember in the BRDF equation, you have the incoming direction and the outgoing direction. So this is the incoming direction. The direction towards the light is the incoming direction. And that is what we are perturbing slightly. So that way we'll be able to sample many points across the light. And because we know that only the visible part of the light is contributing to the shadow or not, we can take advantage of this cone sampling to send samples only in that region rather than sampling the entire sphere of the light. So we could do that also. We could just randomly sample the entire sphere, and that will still give you okay results. But by narrowing it down to the area where we know that that this cone region is the only place where the samples can come from and that contribute to the light, we can take advantage of that. So that is importance sampling. Importance sampling the light is what we are doing here. It's very similar to how we sample materials for using the BRDF. So let's try to do that. And I have shared with you another fork of the shader that we were working on last time. This is called Class 7 Soft Shadows. You can find it on my profile. It should be public. I'm going to save it. So the code is very similar. What we have done new in this part is a little bit of in the scene. I wanted the light to be visible, so I made an extra sphere, which we can see that it's there, and I made the light as well. So this lights are invisible because we're not drawing them, but I wanted to have some representation of the light so that you could see it. So as the 10th sphere, I just add a light and I make it so that it moves, and I make it very bright white color. So that's the change. So there's an extra material somewhere or extra sphere somewhere at this location at frame 0. So it's somewhere a little bit down the z-axis and halfway up. So you can't probably see it because it's small, of radius 0.2. So let's so that's one thing, and we'll reduce the number of samples so you can see the difference. So we'll make it like 1 for now, so it can run. Next part is, so this loop remains the same. So again, I go over this again and again because just to emphasize like how simple the loops are. So we already have 2 loops that are running behind the scenes because of shader toys. So that goes through every pixel in X and Y. So when you get to this main image function, you are looking at 1 pixel. And that pixel's coordinate is in the frag coordinate. And we're supposed to figure out the color of that pixel. So 2 loops are already taken care of for us. And within that pixel, we are going to run a number of samples. And within each pixel, we are going to perturb it slightly using this random number to generate multiple random samples per pixel. So you'll hear this called as SPP many times in other ray tracers. Samples per pixel is SPP. And then we adjust for the aspect and other things. And so now we create a ray that goes from the eye through the pixel. And the eye is at 0, 0, 0. And we create this ray in that direction. And next, we have yet another loop, which is going to bounce around. How many times to bounce around for collecting more information. You can change that, but that's set to 2 for now. So then for that ray, we intersect all objects, find the sphere that intersected with it. And what we are going to do is, if that sphere is a light, because remember, we added the 10th sphere as a light, and it's the first bounce or the 0th bounce, then we just return the color of the light, which means we're taking the ray and we're hitting the light directly. So that's where the light happens to be, and we hit it by the first ray that gets out of the pixel. Then it means we are seeing the light. So we'll just show the light, and the color for the light is what is returned. And and we don't do any other computation on that particular sphere because we just want to treat it like a light, as a white object. We don't have material on it. It could have material, but for our simple case, we will just ignore it and get out of the loop. So that's just a simpler setup. And then we find the hit point and do some calculations for the normal at the hit point, the vectors, find the tangent and the binormal, because that's what is needed by the BIDF calculation. Basically a coordinate frame that is on top of the intersection. So next, what we do is we sample the light. So the formulation that I described to you just a few slides ago is what we'll use here. And what this would return is the color of the light, and also 2 other things. It will return to us a new direction, because remember, we are going to perturb the direction slightly based on where we want to sample within that cone. And it will also return to us the light PDF. And I'll talk about this, what this means, which is the fractional contribution of that particular ray. So we keep accumulating that as well. And secondly, we want to check if the light is visible at all or not. So if the light is not visible, which is a full shadow, then we can just multiply that by the incoming color, and that will become 0 essentially if it is 0 or 1. So it's a Boolean, but we're returning it as a float. So next, what we do is we compute the BRDF at the intersection, and this will give us the properties of the material, and then we do the cosine rule of how much of the BRDF to take in, and then if the light is visible, we will take the accumulated PDF and then divide by that. So just hold on to that thought. I'll explain to you what this PDF portion is. And then that's it. So then you accumulate that. And as you accumulate it, then you want to shoot another ray, basically in the perturbed direction. So this function here, sample light, it is going to take the ray that is going out to the light, and it will move it slightly so that you get different samples. And that is the direction that you get out of the sampling, and that's where you will go for the next ray. So you go hit the light, and then you take that vector and change it slightly from the next point onward. So you keep doing that until you accumulate more and more light. So if you don't hit anything, you just return the background color, and then ultimately, end of all the bounces, you have accumulated everything, and you divide by the number of samples, and tone map it, gamma correct it, and display. So that's all there is. So we'll cover a little bit of that math on how to sample that light, and I think I described to you the equation, but let's run this and see what happens. So when I run this, so remember I'm moving the light in the Z direction slowly with frame over 200. So you should start seeing the shadows. There is some floating point inaccuracies here and there. As you can see, you have these softer shadows now. So there's not enough samples, so it's a little bit, but it's softer than before. So what has happened is, because this WI that we added in is slightly perturbed, it is going to give you those soft shadows. So we can check for that, like by just commenting it out, and then instead of perturbing it, we just go towards the light. Say, that didn't work. Okay, so let's look at the sampling, how we did that. So the sample light essentially follows the formula that I showed here, which is this part. So you're going to transform the whole coordinate system into a cone, and then from there, you perturb the direction a bit. Back to the code. So I'm not going to cover the entire math, but it's the general idea is to take the incoming direction, make an orthonormal basis, and then do all the math, and then sample that cone instead. So instead of sampling the entire sphere, we just narrow it down to the cone, and within the cone. So because you have this random vector here, that is going to be used to perturb the ray slightly. So that's about it for the sampling part. And then the visibility is easy because all you're doing is trying to intersect, see if the object did intersect or not. So remember last time when we did the sharp shadows or the point light shadows, all we did was intersect with the light position. But this time we're going to intersect with all the objects and see, because it's a sphere, so we can see if this was the light and it is visible. We can easily tell that. So we'll have to use this function to intersect with all objects and find out if the whole object was intersected and not just the one point on the light that we did last time. Any questions on this so far? All right, looks like no questions so far. So let's talk a little bit about the PDF that I had in the code. So the general sampling strategy is that if you know the CDF or cumulative distribution function, then you can always generate a random sample from that. So here is a great example. So I think what you have is a probability distribution of an exponential function, and you integrate that, and then you find the cumulative distribution, and you invert it, and you find the inverse CDF, and this is what you would sample. So U then can be sampled uniformly by giving U in the range 0 to 1, and by computing this, you essentially get samples from this particular distribution. So that's the entire idea of, like, it's not necessary to just have a BIDF. You need to be able to have some kind of a PDF or probability distribution function that you're sampling, and for that you would need some kind of a CDF or an inverse CDF. So so that becomes challenging because not only, like, if you look at all the components of the BIDF, there are so many. So where did it go? So all these components of the BIDF, they have their own PDF and CDFs that you would need to sample and compute. So there are at least 3 or 4 things that you would have to have PDFs and CDFs for. So, and then the researchers and other people, they have worked it all out for all of these popular BIDFs, what the CDF is, what the PDF is, and the idea is the same, like exactly what we did for the light sampling. It is to take this into some orthonormal basis, and then find a point that is that can be driven by UV or the random perturbation, and then that will give you the sample that you desire, which is like slightly off and slightly different. But then at the same time, you need to weight that sample with the inverse PDF so that you know how much it is contributing. So that's where you have this 1 over PDF in the numerator there for sampling the light. So you'll have the similar strategy for all of these components of the BIDF, but there are 4 or 5 of these things that you would need. And we're not going to go into the details of this, but I wanted to show you an example. So I did a search on shader toy, and I found this example where somebody has done that and implemented. So I don't know who this person is. Ivan Safrin. So again, just showing his shader toy. So he's doing all of these things where you can see that he's important sampling the GGX part. He's important sampling other things. So these are, again, a different BRDF, not the one that we have been using, but a similar idea. So they do the exact same thing where you do the importance sampling, you take the random number, and do all these calculations. So, and what they have done here is they've sampled it separately. So you'll see that each of the BRDF has its own sample count. So you're doing this sampling for multiple samples per BRDF. And then same thing with the light. They are sampling the light separately and doing multiple samples per light. In a general system, you just want to let the samples run all over and then assume that it will cover everything. Because in a general system, anything can be emissive, but it's if you know that things are lights beforehand, then you can sample them directly, like we did, or like this code is doing. So this this has integrated the mouse coordinates, so you can go up and down to increase the metallicness, and left to right to increase the roughness. So they also have a texture which is available here that is being projected on the material. So it's kind of a nice example of how you can import and sample the BRDFs as well. So let's go back. So that's what you'll see. I think this is, just keep in mind that you need these couple of functions per attribute of the BRDF that you want to sample. And then you can then start creating the additional directions that you need. So essentially, the BRDF tells you which direction to go next. And sometimes what will happen is the material is composed of a complex BRDF. It will have multiple properties. So it is metal, it is rough, it is also specular. So how do you reconcile that? And that's where multiple importance sampling comes in. So in case of multiple importance sampling, you can do something simple where you can send out 1/3 of the time. So you have 4 attributes. You can send out 1/4 of a time to each attribute randomly, or you can do real multiple importance sampling where you figure out the weights of each of these. And so that involves a little bit more math, but that's what people do in practice. So the general rule is that you want to importance sample because you don't want to waste your rays. The rays are precious because the more you have, more time it takes to compute them. And then if you waste them, then you're not converging fast enough. So you're not seeing the results. You're shooting them in directions which are meaningless. So for example, the cosine theta rule, what it helps us do is not shoot as many rays along the horizon, because that's very unlikely to contribute much. So so just doing that actually helps you kind of use the rays more effectively. So when we use BRDS, we are essentially targeting our directions, like where to go. So more you know about your scene and lights through these BRDFs, the better you can be about where to send the rays. So that's the general idea. So that brings us towards the end, and let's see what we did so far. So what essentially we did in that loop we had, that's right here. So we are, for a number of bounces, for a number of samples, we're going around intersecting the ray with the object, and then with the light, and then finding the BRDF and computing that and accumulating that as we go on, and change the direction of the ray slightly, and then repeat for the number of bounces. So that's it, right? So that's the loop. And what that causes is we are taking the incoming light going to the viewer and angle to the normal, and we do this over multiple bounces. And if the object were to, say, emit light, like light emitting objects we were also doing sampling for, we could just add the emitted light as another thing that get added to the pixel color. So that's the entire thing we are doing. And that looks suspiciously similar to the rendering equation now. So I said in the beginning, in the first class, that we will not do the rendering equation route, but we have arrived at it through experimentation, through just intuition and reasoning. So this is exactly what we're doing. So this part, the function f here, is actually the BRDF. And this part is the reflected light. And the cosine theta is the angle. And this is the emitted light if it was a light emitting object. So this is exactly what we did without having to go through the integral. But I think the integral kind of ties everything together mathematically. So I urge you to kind of go back and kind of take another look at it and see in terms of what you have learned so far and how we achieve that without having to kind of solve that. So when we do multiple samples per pixel and multiple light samples per pixel, multiple BRDF samples per pixel, we are essentially doing the integration. So doing integration by something called Monte Carlo. So the Monte Carlo method is a sampling method where you can repeatedly take samples from a distribution, and then when you average them over many samples, then essentially you're solving an integral. So Monte Carlo ray tracing is essentially what we have achieved and solved this rendering equation per pixel in a more discrete form. So that brings us towards the end. So this is one more slide I wanted to show you. This is from my friend Julian Fong from Pixar. He put this together in more of an idea of like an XKCD comic, and he explains it in a few common words what the rendering equation means. And I think it's similar to what I said just in the previous slide. So take a look at that. Next is what do you do after this course? So there's so many possibilities, and you could follow Pete Shirley's ray tracing series. So he has 3 books in the series, ray tracing in a weekend, and another one, and another one. And if you Google, I think it pretty much for every platform people have implemented, from Rust to Python to RTX cards, and so there's many implementations available for all his code. All his books are free, and all the code is available. So it's an amazing resource to kind of just dive into deeper into how rendering works. And I think the last book in the series, Ray Tracing for the Rest of Your Life, it has some pretty advanced material. That's awesome. So then there is the PBRT book for practitioners in the field. It is one of the most detailed books I have seen on ray tracing. It's called Physically Based Ray Tracing Book. And it's pretty much the Bible for ray tracing. It's got a lot of examples, a lot of code, and it's also free online. I think one of the editions is free. So I put links to all of these in the slide. You can go and check it out. So once you understand, once you write your own renderer, play with it a little bit. So, and when you want to go like big, when you want to like leave all the basics to be managed by an API, you can start using Embry or Optics or Vulkan. So I think the Vulkan and DirectX are still lower level. Optics is high level to interface with RTX. Embry is similar, but for CPUs. It's from Intel. It's free, so you can just download it and play with it. It is very good in terms of like it'll take care of all the traversal and intersections for you. So you just have to provide some kernels for shading and other things. It's very performant. You can like render millions of objects with it in real time almost. So check it out, and both of them actually come with some denoising as well. So you don't have to use 100 SPPs. You can stop at 64 and then denoise the rest of your image. So check them out. They're pretty useful. Other places to learn are from papers. Papers going as far back as Turner Witters' paper. I think it's a simple idea, implemented, still works. You can try to implement some of those ideas. Jim Kajia's paper on the rendering equation, or even older papers that kind of talk about like how light works. And a lot of this theory comes from sampling from the Monte Carlo side. It's very, very old technology or research, but then applied anew for different purposes. You can go to conferences. SIGGRAPH is just around the corner. You can meet a lot of people who work on these things and ask them questions and get your curiosity satisfied with about ray tracing in general. So again, there's a ton of resources out there. Don't be shy. Just try them out. And if something doesn't work, or you're not good at Python, you don't learn it, you want to stick to C++, try something else. It's all available. So I think there's probably no excuse. So what I think what Eric was saying earlier, like you want to like start building some sort of portfolio or a website where you have interesting images, you have interesting insights on thoughts. So you can start putting together, start contributing to some open source project, and small little bit here and there, and just gain insight into how things work and what to do. So that is all I had to talk about. Next, I will take any questions, and if you want to remain connected with me, you can connect with me on Twitter or find me on LinkedIn. I think it has been an awesome journey so far. I think with you for 7 classes, and in the first class we did pure sampling, and I stated that simple sampling is essentially a ray tracer with parallel rays and objects stuck to the screen, which is true actually. So we wrote our first ray tracer on day 1, and then over time we made it a little bit better, added more things to it, multiple objects, reflections, BRDFs even, shadows. So it's pretty remarkable what we could achieve in a 7-hour course. All right, any questions? Is there anything we need to change to support area lights that aren't spheres, example, rectangles? So yes, so first of all, you need to implement a rectangle ray intersection to find out if your light is getting hit or not. So that's the first thing. And secondly, you would need to change your PDF because actually for rectangles, it's simpler. You could simply use the rectangles area and the fraction, because in this case, it won't be a curved surface, so the projection is easier. You can find the relative area. So to start out simple, you can just use the proportion of the area that is visible, and that should work. That should work well enough. If that doesn't work, you can use random sampling of the rectangle, and that should work. Random uniform sampling, so you cover most of the sphere. If that doesn't work, you can go even simpler. You can assume there are, say, 9 lights in the rectangle, right? So you have, and you can hit each of them and see if they are visible or not. So if out of 9, 2 are visible, then the proportion that is visible is probably 2 out of 9, 2 over 9. So that's how you kind of simplify things until you understand and how they work, and then you can make them more complex as you go along. So what is a good source of learning about Monte Carlo integration for ray tracing? So, well, we did Monte Carlo integration. We didn't call it that because I wanted to keep the math away, but you can actually just Google. Wikipedia itself is a great source of Monte Carlo integration. Monte Carlo integration comes to us from, well, from the atomic research years ago. And it was used to find out like how the atoms move, and instead of trying to figure out a statistical distribution, you could just sample it And it's a common practice to solve integrals using Monte Carlo. Anything else? All right, so if there are no more questions, let's end here. And please stay connected, and I want to see what you guys do. So thank you again for being on this journey with me. Bye-bye.
At SIGGRAPH 2020, more than 10,000 individuals from 95 countries gathered virtually to experience over 350 hours of content presented by more than 1,600 contributors. What resulted was pure SIGGRAPH. Robotic advances use subtractive fabrication techniques to carve foam and similar materials like an artist. Modeling and predictive computation creates a more robust and accurate time-stepping of nonlinear elastodynamics. New investigation into damage simulation could change the landscape of video and game effects, as well as surgical training. Novel healthcare technologies point toward new ways to transform and enhance lives. Research will help users to create reprogrammable multicolor textures made from a single material. AI-driven technology pushes the capabilities of crowd simulation. Award-winning animation showcases the latest in computer graphics. Real-time and gaming technology advancements transform interactive storytelling techniques and explore new applications of the technology. Evocative digital artwork uses machine learning to create visceral experiences. Now is the time to share your research, your innovations, and your creative inspiration. SIGGRAPH is your community, and we hope you'll share your work with SIGGRAPH 2021.